All right, so we're going to work the last 3 in-class problems, which can be found on the last page of your packet, page 6. First, number 17 and 18 are solution problems. We've already done similar ones in class and earlier in class problems, but it's definitely worth taking a look at again. So number 17, Demo has a 6 molar hydrochloric acid solution. For her classes, she needs 1 liter of 0.5 molar. How would she make it? So first we need to do the math to figure out how much of the stock we need, and then I need a description of what is required to make the physical solution. So looking at this, this is a dilution problem because we're going from something of a higher concentration to a lower concentration. So we're going to use M1V1 equals M2V2. We are going to plug in what we know. We know that we have a 6 molar solution. We want to know how much volume of that would be required to make 0.5 molar solution in a quantity of 1 liter. When we solve for volume here, we end up with a liter measurement of 0.0833. That's kind of tough to measure, a liter. So we're going to go ahead and change it to mils, and it'll be 83.3 mils is required. If you stop here, you've only done half the work. Again, I need a physical description of what you do to make this solution. So you need to write a statement. Place 83.3 mils of 6 molar HCl into a 1 liter flask and fill to the line with water. Again, fill to that 1 liter mark. You can also say QS, that means fill to the line. All right, for number 18, 18 is another solution problem. This time we're making a solution from a solid, not from another solution. So we're just going to outright find how many grams of that silver nitrate do we need to make a 0.5 molar solution, and we need 500 mils of it. So remember, molarity is equal to moles, in this case, of silver nitrate over liters. We do have the known molarity. We don't know how many moles of silver nitrate we need, but we do know we want to make 500 milliliters, which is 0.5 liters. When we multiply to solve for moles, we get 0.25 moles of AgNO3. And we know that moles is equal to grams over molar mass. Another way to remember it is just knowing molar mass is grams per mole, and you can solve using dimensional analysis. But with this, I'm just going to go ahead and plug in what I know. I have 0.25 moles. I know the grams is what I'm looking for, and my molar mass of silver nitrate is 169.87 grams per mole because I added it up from the periodic table. When I do the math and solve for grams here, I get grams being equal to 42.47. Now, again, I need some sort of statement. So I'm going to say place 42.5, we'll round to 366. We'll pretend this is 366. 5 grams of silver nitrate in a 500 ml flask. You can see over here to the left, you've got all sorts of flask sizes. Here's our liter that we used in problem 1. This is the 500 liter we're using now. We're going to place those grams in that flask and then fill to the 500 ml mark with distilled water. And that's how you make your solutions. So you can definitely expect to see something like this on your test. All right, let's work this last problem. This last problem is a little long, but it's really nothing that you already haven't done. And so I'm going to read it first. Potassium dichromate in an acidic solution is frequently used to determine the concentration of Fe3 in solution. An equation is given you to represent what's going on in the actual titration that's happening here. A solution of dichromate is prepared by dissolving 6.42 grams of potassium dichromate in 800 mils of water. A total of 21.35 mils of this solution is required to reach the endpoint in a titration of 250 ml sample containing Fe plus 2. Determine the concentration of Fe plus 2 in the solution. Well, the gist of what's going on here is we're making a stock solution of this by mixing this stuff together. Then we're taking this stuff, putting it into a burette, and titrating with a beaker that has 250 ml solution of that iron plus 2. Our job is to figure out what the concentration of this iron plus 2 is. And there's a few problems that I already can tell. First off is looking at that equation. We can't do a titration or any sort of experiment unless we have a balanced chemical equation. So we're going to have to do a little bit of balancing first. And since we're in an acidified solution, we're going to go ahead and do balancing through the half reaction method. So looking at this equation, the two things that are changing oxidation state are your chromium and your iron. So I'm going to go ahead and do the half reaction for, I'll pick chromium first, no reason, I'm just choosing to do that. Cr2, oops, let me move it over a little bit so I have room. You'll need a big piece of paper for this. I'll end up erasing so I can fit other things on here. But for now, Cr2O7 negative 2 goes to Cr plus 3 plus 7H. Oops, sorry. I'm copying what's on my paper as opposed to showing you what to do because I forget you all are listening to me. All right, Cr plus 3. So the first thing I do was pull down everything that had Cr in it, which is that. Now, to balance this half reaction, I balance everything but H's and O's. So I put a 2 there, and that's balanced. Now I balance O's using water. So I'm going to put 7 waters on the right side. And then I'm going to balance H using H pluses. So I'm going to put 14 H pluses on the left. My overall charge on the left side is a plus 12, and on the right it's a plus 6. So looking at this, I am going to balance by adding 6 electrons to the left. My next step is to balance the other half reaction. Iron plus 2 going to iron plus 3. Balance everything but H's and O's, done. Balance O's are done, H's done. Now we have to balance electrons, so I'm going to add 1 electron to the right. In order to add these up, I'm going to multiply the bottom by 6 so I can have a common factor of electrons, and I get that many electrons. So when I add these up, my electrons cancel. I have 14 H pluses plus Cr2O7 negative 2 plus 6 iron plus 3s, and that gives me 2 Cr plus 3s plus 7 H2Os plus 6 iron plus 3s. So all I have to do is take these coefficients now and put them into the equation above. I have a 1 there. In front of my iron 2, I have a 6. These are really the only 2 coefficients I'm concerned with because I'm looking for the relationship between this and this. But I'll go ahead and finish writing them. 14 goes there, 2 goes there, iron 3 is a 6, and water is 7. So that's my balanced equation. Those of you at home might want to stop the video now and get out another sheet of paper because we're going to now start the actual work of this problem. And I will erase this right now. Okay, so to begin the problem, first thing I need to realize is that I'm making the stock solution. In the stock solution, I've got 800 mils, and I'm dissolving 6.425 moles of K2Cr2, so potassium dichromate. My first step is I need to find the molarity of the stock solution. It's useless if I don't have the molarity. So to find molarity, I remember that molarity is equal to moles per liter. I'm going to do this with dimensional analysis just because the last problem I did formula, so I'm showing it both ways so everyone can see a different way. I start with what's in my solution. Currently, I have 6.425 moles of this stuff in 800 and 800 mils. Well, I'm sorry, and it's not even moles. I make mistakes even when I have a piece of paper in front of me saying otherwise. Isn't that amazing? Okay, so right now that's how many grams per mil that this says I have in solution. So what I need to do is convert this to moles per liter. So let's take care of those mils first. For 1 liter, I have 1,000 mils. What this does is it gets me in a per liter situation, so that's good. Now I've got to convert my grams to actual moles, and I use the molar mass to do this. So for every, here we go again, here comes the mistakes. I'm going to convert grams to moles. For every 1 mole of potassium dichromate, I have a molar mass of 249. So 249 grams per every 1 mole. When I do the math, I get an answer of 0.0323 moles per liter, and that is my molarity. If you didn't like solving it this way and you wanted to do dimensional analysis, you could have first converted the grams of potassium chromate to moles directly, just using your simple grams per molar mass, and then take those moles and then divide them by liters. And that would have given you your molarity that way. I just did it all in one step instead of two. So now that I know the concentration of this stuff, I'm going to take this stock, which now I know the molarity is 0.0323 molar, and I'm going to put it in a burette. And I'm going to titrate it. And I'm going to titrate it into a little flask that has 250 mils of my unknown molarity iron in here. Iron 2. I don't know the molarity of that, of what's in that beaker. I do know when I titrated, I found that I reached my equivalence point when I used 21.35 mils of my stock. All right, so what I need to do first is go ahead and find moles of my known, which is my dichromate. Well, I know molarity and I know mils, so now I can very easily find moles. So let's go ahead and start doing another dimensional analysis here. Mils isn't very useful when I have molarity, so for every 1 liter, I have 1,000 mils. And now I can place my molarity in here to convert to moles because I know my molarity is 0.0323 moles per liter. So this will give me my calculated moles of potassium dichromate. 6.90 times 10 to the negative 4th, Cr2O7 negative 2. Now there's a little issue here. I just want to point this out to you. What we actually found here was the molarity of potassium dichromate. So technically this is really the moles of potassium dichromate, not just dichromate. But we are lucky enough that for every 1 mole of potassium dichromate, there's 1 mole of dichromate, so it's the same 1-to-1 ratio. Had this been a potassium concentration we were looking for, we would have had to multiply it by 2 because for every 1 of these, there are 2 of those. But we're good to go in this case since there's 1 dichromate in every potassium dichromate. All right, now we have moles of this to be 6.90 times 10 to the negative 4th. This just becomes a normal stoichiometry problem now. We have moles of known. We've got to get to the moles of our unknown through dimensional analysis. So 6.90 times 10 to the negative 4th moles of Cr2O7. Through our balanced equation, you guys saw that for every 1 mole of the dichromate, let's not forget our negative 2's, we have 6 moles of Fe plus 2, which gives me 0.00414 moles of Fe plus 2. Okay, we're almost there. we have moles, but again, the problem says concentration. So we have to divide by a volume. What volume do we divide by? Well, what did we dissolve, or what was the iron dissolved in? We were titrating a 250 ml sample. So we take the moles, 0.00414 moles, and divide it by 0.250 liters. When we do that, we end up with 0.0166 moles per liter of Fe plus 2. And that is the concentration of our unknown. All right, that's it. Good luck studying.